Okay, so let's look at derivative for a second. And geometrically, whatever curve we have, all we're doing, if we want to know what the derivative is, the derivative is just what we call what? The rate of change, right? Which should be a familiar phrase to you. Okay. So let's say we're picking a point here. In algebra and pre-calculus and all of that, you should know by now that the rate of change is the slope when we talk about linear functions. Y2 minus y1 over x2 minus x1. Why I started to write a y. Okay, now with a linear function, the rate of change is always constant. It's the same. The slope stays the same for the whole thing. That's not true when we have like a little curve, right? So let's say we pick a point here and a point here. We can talk about a secant line going through here. Okay, and we can look at the slope of that. Now the slope of that then would be, now we're just going to move over just a little bit, some arbitrary amount. So let's just say we can move over h. Okay, so that point would be c plus h. So the x-coordinate. So then we would have f of c plus h is the y-coordinate. Now this little point down here then would be c and f of c. All right, so wherever we evaluate that function at. So for that secant line, the slope of that would be f of c minus f of c plus h divided by c minus c plus h, right? Or we could simplify. Let me careful here. Now we could change the signs a little bit and say, okay, well that's f of c plus h minus f of c over h. Now, we could play that same game and we could move this point closer. All right? Okay, so in this case, h is smaller. We move it a little closer. Then we could move it even closer and say we had draw the line in between there. And h gets smaller and smaller as we draw that point closer until such a time. Now let me kind of erase these so I got some room. We get a tangent line. So now the slope of the tangent line, where it only touches in one spot, is the rate of change for that function. Okay? It's the slope of the function at that specific point. Now, as soon as you move, the slope changes, right? And you would wind up with a different tangent line. So what's happening, and the only difference is we're moving this h a little closer and closer. So that's how we define the derivatives using this difference quotient, the slope formula. And we would say, okay, well, that's the limit as h approaches 0. So a function, the derivative at a point, is the limit as h approaches 0 of f of c plus h minus f of c all over h. And it's just the same thing. It's a combination of things that you've done, right? You've been finding slope for a long time now, because that gets introduced way back in like your first algebra class. Okay, at the beginning of this class, we introduced limits, right? So it's just a combination of your old formula for slope and the idea of a limit. So let's get a specific example and say, okay, well, I have a function, and let's say it is 3x minus 2. Okay? And I want to know what's the derivative when x equals 5. Cool. Okay, so we'll do f of 5 plus h. Okay, oh, wait a minute, I forgot to write down my limit. Limit is h approaches 0 of f of 5 plus h minus f of 5 all over h. Now, we can go ahead and substitute those values in for our x, because that would be 3 times 5 plus h minus 2 minus then f of 5 is just 3 times 5 minus 2 all over h. So just simplifying a bit. So we get 15 minus 3h plus 2 there. And then 15 minus 2 would be 13 for h. Now, those 15 minus 2 is 13 minus 13. So we get limit as h approaches 0. That really was a 0, not a 2 there. Of 3h over h, which then is, approach 0, just 3. So the limit, it's a constant. So the rate of change for that function is a 3. Now, I picked a linear function because we already know from past experience that that number is the slope, right? So I'm just using this to kind of verify to you that the formula works. Okay? We know the slope is 3 at that point, and in fact, at every point for a linear function. So whether I put in 5 or 12 or whatever, it better turn out to be 3. So let's do one that's a little bit harder. Okay, one that has something that's changing. So suppose f of x equals x squared minus 1. And we want to know what is the rate of change, the slope, the derivative, whatever you want to call it, at negative 2. So we're going to have f of negative 2 plus h minus f of negative 2, the difference in the y-coordinates, over the difference in the x-coordinates. And we want the limit as that difference in the x-coordinates gets closer to 0. So that's going to be 2 plus h squared minus 1 minus, and then f of negative 2 over h. And I got to have my limit out front. I'm being very bad about leaving that off, apparently. Don't do that. So simplifying things a bit. All right, so if I simplify this, we get 4 minus 1 is 3, minus 3. Okay, so we're going to be left with negative 4h plus h squared over h. Well, I can then reduce that fraction because there's an h in both of the terms in the numerator. Now it's a continuous function and stuff, so that's just going to be negative 4 because we put 0 in for h. So what that's saying is on this graph, x squared, what was it? Minus 1. Okay, on x squared minus 1, that's going to be a parabola that looks something like this. And over here, where x is a negative 1, the slope of that is a negative 4. So that's the derivative of a point. Now we can use this same idea to talk about a derivative of the function. Okay? Now the only difference is we go through this process and we don't pick a specific point. Okay? So the derivative of the function is just f of x plus h minus f of x all over h. See, we're just going to leave the x's in, and then we're going to evaluate it, and then we're going to have like a formula for the derivative, right? So that way we can evaluate that formula to find out what the derivative is at any point without going through limits over and over and over again. Okay? So again, let's just use that same last example so we can kind of compare it. That was x squared minus 1, right? So limit as x approaches 0, and we're going to have x plus h squared minus 1 minus f of x, which is just x squared minus 1, all over h. Now when we go to simplifying things, limit as h approaches 0, see that's going to be x squared plus 2xh plus h squared minus 1 minus x squared minus 1 all over h. So the x squareds are going to be nice. That's 0. The 1s are going to cancel out because you get negative 1 minus a negative 1. And that just leaves us with then 2xh plus h squared all over h. And again, we can reduce that. And that's going to be 2x plus h, which is just going to boil down to 2x. So the derivative of the function f prime of x is equal to 2x. Now just to verify what we did before, if I want the derivative at, say, negative 2, that just means I can substitute that in and see we get the negative 4 like we did before. Or perhaps I want the derivative at 1. Well, that would just be 2 times 1, which would be 2. So looking at that graph again, if we have our parabola and we look at positive 1, then we look at the slope here of that tangent line, which is the rate of change of the function. That slope is 2. Okay? So that's how we find the derivative of a function and the derivative of a function at a point, and kind of what we're looking at. Now, we are going to get easier ways to do this stuff in upcoming weeks. This is the definition of it, and there are lots of functions out there where we have to rely on the definition. There are not shortcuts for everything, okay? What we're going to be doing here shortly is learning shortcuts, but they only work for particular types of functions, okay? So that's where you need to be careful, and that's why it's important that we know the definition of it, because the definition always works, okay? The shortcuts don't necessarily always work.